Welcome viewers. In this video we'll see the solved problem in the magnetic circuit part 4. Some more problem available in the other part. The link is given in the description box. Subscribe this channel for more videos and course material. The course material drive link also available in the description box. Now we'll go to the problem 1. An iron ring prepared from a 10 millimeter bar has an average diameter of 8.3 centimeter and is wound with 598 turns of copper wire. A current of 0.975 ampere is sent through it. Find the flux established by the current. The take mu r, relative permeability, equal to 875. So we need to find the flux developed. The data is given is number of turns is given 598. The current is 0.975 amperes. And the mu r value is given 875, and mu naught is constant 4 into 10 to the power minus 7. The diameter is given 8.3 centimeter, diameter of the iron ring. So that radius equal to 8.3 divided by 2, 4.17 centimeter, 4.15 centimeter. So while converting meter, it is 4.15 into 10 to the power minus 2 meter. So our aim is to find the flux density. Find the flux established in the iron. So first we will find the area of cross section. The radius is given, so area equal to pi r square, pi into r. R is 10 into 10 to the power minus 3 square divided by 4, that is equal to 7.85 into 10 to the power minus 5 meter square. Right? So the average diameter is given 7.85 into 10 to the power minus 5 meter square. Then we will find the average length of the magnetic path. Average length of the path is nothing but circumference of the ring. Circumference of the ring is nothing but the length. L equal to 2 pi r. So 2 into pi into 4.15 into 10 to the power minus 2. So this radius refers the radius of the ring. This radius refers the radius of the coil. Radius of the coil, pi r. So by simplifying this, we got L equal to 0.267 meter. The length of the magnetic pole is calculated. Now from that we can easily calculate the flux available in the magnetic path. Flux equal to mmf divided by reluctance. The mmf is nothing but N into I. Reluctance we can write L divided by mu naught mu r into A. The formula is available. So this mu naught mu r A will go to the numerator. So N into I mu naught mu r A divided by L. Now we'll substitute the values one by one. So the N is nothing but 598 number of turns. The current equal to 0.975 amperes. Mu naught is 4 pi into 10 to the power minus 7. Mu r value is given 875. The area what we calculated 7.85 into 10 to the power minus 5. The area we calculated divided by the length of the core is 0.2607. So by simplifying this, what we got 0.193 milliweber. Milli means 10 to the power minus 3. 10 to the power minus 3 is written as milliweber. So now we calculated the flux established in the iron core is 0.193 milliweber. Now we'll go to the second problem. A 100-turn coil is wound on a magnetic bar. The average diameter of the coil can be taken as equal to 10 millimeter. So this diameter is the diameter of the coil. Find the EMF induced in the coil when the flux density B is changed from 5 milliweber per meter square to 0.1 Weber per meter square in 35 nanoseconds. Now we'll see the data. What are the data available? So the number of turns is given 100 turns. The time taken to change the flux is 35 nanoseconds. That is 35 into 10 to the power minus 9. Nanosecond means 10 to the power minus 9. The diameter of the coil is 10 millimeter. So the radius is diameter divided by 2, 5 millimeter. So 5 into 10 to the power minus 3 meter. Millimeter is converted into meter. Then the flux is changing from two different value. First we will take this B1, it is 5 milliweber per meter square, that is 5 into 10 to the power minus 3. Milli is converted as 10 to the power minus 3 Weber per meter square. Milli is written as 10 to the power minus 3. And B2 changed to another value is 0.1 Weber per meter square. Now we need to find what is the EMF induced in the coil. So based on the given data, first we will find the area of cross section of the coil. A equal to pi r square. Pi into 5 into 10 to the power minus 3 the whole square. The radius of the coil. This is the radius of coil. So by simplifying this, what we got? 78.5 into 10 to the power minus 6 meter square. Area of cross section of the coil. Now from then we will find the flux. Flux density is given. From that we can able to find flux. Pi equal to B1 into A. So B equal to pi by A. So that pi equal to B into A. So pi 1 means B1 into A. The B1 is given as 5 into 10 to the power minus 3. The A is this value calculated 78.5 into 10 to the power minus 6. 5 milliweber per meter square given. So 5 into 10 to the power minus 3. So by simplifying, what we got? 0.3925 into 10 to the power minus 6 Weber. The flux in the first due to the first one. Similarly, the second flux pi 2 is nothing but B2 into A. The B2 value is given as 0.1 into this area 78.5 into 10 to the power minus 6. So by simplifying this, what we got? 7.85 into 10 to the power minus 6 Weber. The pi 2 also we calculated the pi 2 value. Now the change in flux, the difference between these two, pi 2 minus pi 1, 7.85 into 10 to the power minus 6 minus 0.3925 into 10 to the power minus 6. These two values, pi 2 minus pi 1. So the resultant will be 7.4575 into 10 to the power minus 6 Weber. The change in flux is nothing but this value. So by using that we can find the EMF induced in the coil. EMF induced in the coil equal to N into d pi by dt. Number of turns into rate of change of flux. So the number of turns is 100 into this change in flux is nothing but d pi 2 minus pi 1. So 7.44575 into 10 to the power minus 6. Divided by the t, time is given 35 nanoseconds. So 35 into 10 to the power minus 9. So by simplifying we got 21.307 into 10 to the power 3. So this 10 to the power 3 we can multiply that, so that 21,307 voltage. The EMF induced in the coil is 21,307 volt. The more problem available in other videos, the link is given in the description box, and also subscribe the channel for more electrical videos. Thank you.